This is problem 5 of the 2022 MMATHS Individual Round, and the problem reads, holding a rectangular sheet of paper ABCD, prior folds triangle ABD over diagonal BD, so that the new location of point A is A prime. She notices that A prime C is equal to 1/3 BD. If the area of ABCD is 27/2, find BD. All right, so let me draw our rectangular sheet of paper, and we're going to label its vertices A, B, C, and D. So A, B, C, D. We draw by diagonal BD because we're going to reflect point A across it. So A would go around somewhere over here, like right about here. We're going to call this A prime, and note that A prime is the reflection of A across this diagonal BD. So we want to find the diagonal BD given a few things. First of all, we know that A prime C, this length, is 1/3 the length of BD. And so let's call this length BD X, and A prime C is 1/3 X, and we're going to try to find X in this problem. We also know that the area of ABCD is 27/2, and remember that the area of any rectangle is length times width. So why don't I call this length little a, this length little b, and we have little a times little b equals 27/2. We can also mark a few other sides and angles as well, since A prime is the reflection of A over side or diagonal BD. We actually see that this entire triangle, which I will mark in red, A prime BD, is actually just the reflection of this triangle ABD across side BD. A gets flipped across BD, so everything corresponding to A also gets flipped over as well. And because this triangle is a reflection of the previous one, they're actually congruent to each other, because flipping a triangle over a line doesn't do anything to change the length of or angles of this triangle. So A prime D is going to have the exact same length as AD, namely A. A prime B is going to have length B. This angle over here, DA prime B, is going to be 90 degrees since this guy was 90 degrees. Finally, let me mark BC with little a as well and CD with little b as well. Okay. And I'll mark this angle 90 degrees as well since it's a rectangle. So first of all, we want to find X, but we don't know a lot about X. So why don't we try to write some other stuff down? Namely, we've got, by our nifty Pythagorean theorem, we look at this triangle. It's a right triangle, ABD, and it has side lengths A, B, and X. So we can use our Pythagorean theorem, which states that A squared plus B squared equals X squared. That's nice and all, but what are we going to do now? Well, here's where I'm going to use this nifty little trick. I'm going to write cyclic quadrilateral. And this term might sound scary, but all it is it's a quadrilateral with a few nice properties, the most notable of which being it can be inscribed in a circle. In this case, I'm going to claim that A prime CBD is a cyclic quadrilateral, so there's a circle that looks like that. And the way we see that is essentially because this angle over here is 90 degrees, and this angle is 90 degrees as well. And if you sort of look at the lengths surrounding these right angles, they sort of both enclose the side BD. And the point is, if you were to draw a circle, which this is not a great circle, but you get the idea. If we were to draw a circle, then this angle would actually sort of be enclosing this arc over here. And this angle would also be enclosing the very same arc. And there is a theorem that tells us that any angle that encloses the same arc would have the same measure. So in other words, because these two right angles both enclose the arc that would go around BD, this quadrilateral A prime C BD is cyclic. So A prime C BD is cyclic. And how can we use that? Well, it turns out there's actually this very nifty theorem called Ptolemy's theorem. So I'm going to write Ptolemy. And what that tells you is that if you have a cyclic quadrilateral, and I'm just going to draw this out right now, and you draw in its diagonals, and you can give these side lengths A, B, C, D, E, and F for the diagonals. Ptolemy's theorem would tell you that A times C plus B times D equals E times F. But given A prime C, B, D is cyclic, we can just apply Ptolemy's theorem on this quadrilateral. And what we see is the two opposite sides have a product of A squared. These two opposite sides have a product of 1/3 x squared because it's 1/3 x times x. And then the diagonals are B and B, so have a product of B squared. So we get this equation. And now I claim this is actually enough to solve for what x is. All right. And how do we do that? Well, we have three equations in terms of three unknowns. So why don't we go ahead and find A and B, and we can use A and B to solve for x. And we have this equation A times B is equal to 27 root 2. We also have these two equations. Well, you see that x squared is equal to A squared plus B squared. So this x squared is also equal to A squared plus B squared. So we can essentially plug in A squared plus B squared for x squared in this last equation. We get A squared plus 1/3 A squared plus B squared equals B squared. And if you expand this all out, you get something like 4/3 A squared equals 2/3 of B squared. And multiplying everything by 3/2 gives you 2A squared equals B squared. You also have AB equals 27 root 2. A and B are lengths, so you could take the square root of both sides to get A times the square root of 2 equals B, and we can plug that back into AB equals 27 root 2, and we get that A times A root 2 equals 27 root 2. So therefore, A squared equals 27, and taking the square root of that, you get A equals 3 square root of 3. So we have A equals 3 square root of 3, and B is equal to A squared root of 2, so B is equal to 3 root 6. Root 2 times 3 times square root of 3. And so we have A and B, and we can plug that back into this equation to get what x is. So A squared is going to be 27. B squared is going to be 3 root 6 squared, which is 54. You can verify these numbers for yourself, and you get A squared plus B squared equals 27 plus 54 equals 81 equals x squared. And since x is the length, we can take the square root of both sides, and we get 9 equals x. So the length of diagonal BD is 9. Thanks for watching, and I will see you next time.